Good morning. In this video I would like to explain analysis and design of synchronous logic circuits. Synchronous logic circuits are also called as clock or sequential logic circuits. They are represented by two models. First one is Mealy circuit, the second one is Moore circuit. We'll see the definitions first. Moore circuit, the output depends only on the present state of the flip-flop. The output depends only on the present state of the flip-flop. That means the output does not depending on the input changes. It depends only on the present state. Whereas the Mealy circuit, the output depends on both present state as well as the input of the flip-flop. Okay, it depends on both input state and on the input of the flip-flop. We'll see that with the help of the block diagram. See, output is depending. You're giving the input to the next state decoder. The next state decoder store the information in the memory element, and the process will take place. So without giving input, you'll not get the output. But here, what does this mean is output is directly affected by the state transition, not with respect to the input change. If you see the same over here in the example diagram, in the example logic circuit, consider X is the input and Y is the output. Consider X is the input and Y is the output. X is given to the flip-flop. The input is given to the flip-flop, but you're getting the change of Y, the output change, with the help of the state transitions, not with the help of input change. Whereas Mealy circuit, if you see the example or block diagram of Mealy circuit, the output of the Mealy circuit depends on both the state transition as well as the input change. If you see, with the help of an example, the output Y depends on state changes as well as the input. So you can have a direct relation between input and output in Mealy circuit, whereas that cannot be achieved in Moore circuit. Okay. Next one is state diagram. State diagram will describe the behavior of the sequential logic circuit. So this state diagram is example of Moore circuit. We know that Moore circuit, the output depends only on the present state of the flip-flop. Consider there are four flip-flops here. There are four states here: A, B, C, and D. So there are four states. We know that Moore circuit, the output depends only on the state change but not on the input. So here the circle is representing the state change. Within that you're going to write the state and its output. If it is A, the state A, output is fixed. For this example. Output is equal to 0 for the specific state A. And similarly for state B, the output is, because the definition says that output depends only on the state of the flip-flop, present state of the flip-flop. Okay. So A, if you consider A, B, C, D are the four states. So each state defines its own output. So A state is resulting 0 as output, B state is resulting 0, C state resulting 1 as the output, and D state 0 as the output. So A divided by output Y. That is what we have to write under inside the circle. And then in order to make these state changes happen, we must have the input. So when you are at state A, please understand that when you are at state A, the input can have two state changes, either 0 or 1. So when you are at state A, and if your X is equal to 1, that is if your input is equal to 1, the state is changing from A to C. And the output is also output corresponding to the state is equal to 1. Similarly, when X is equal to 0, when you're at A, when x is equal to 0, you're going to be at same state A with the with the output change as 0. Next, Mealy circuit. Mealy circuit, we know that the output changes along with present input and state change. So that is the reason each arrow represents x by y here. X by y, we write on the state transition, state change. On this arrow we represent. So here also we consider that there are 4 states A, B, C, D. When you are at state A, if your input x is equal to 0, you're going to stay at state A with output 0. Okay. When you are at state A, and if your input is equal to 1, x is equal to 1, then you're going to have the change from A to B, and the output is equal to 0. Output is equal to 0. And similarly for B, C, D, we'll see that with the help of the state table. So state table consists of the time sequence of input, output, and flip-flop states can be enumerated in the state table. We'll see the state table and we understand how to write the state table for these state diagrams. Okay. Step 1. Obtain the state table from the given circuit information such as state diagram. So examiner will give you the state diagram. So using the state diagram you have to draw the state table. And second step is, if you can able to reduce number of states, try to simplify it. And next one is assignment, that is called state assignment. Assigning binary values to these states are called as state assignment. Next, determine number of flip-flops required and choose a type of flip-flop to be used. And fifth one is get the equations and then draw your logic diagram. That is what is all these steps means. We'll have this example, very important question, damn sure question in your examination. We'll see this example. A sequential logic circuit has one input, one output. That circuit state diagram is shown below. Design the sequential circuit with the flip-flop. So here he has given with what flip-flop the sequential logic circuit has to be designed. So, So this is what is the state diagram that he has given you, Please be very sure. Looking at the diagram, you should be in a position to tell that whether it is a Mealy circuit or Moore circuit. If you find x by y, on these transition lines, then it is called as Mealy circuit. Whereas if you find the output y within the circle, then it is a Moore circuit. Now looking at the question, x by y, that is input by output change is given on the transition line. So it is a Mealy circuit. Okay. Step 1 is drawing state table from the state diagram. So state diagram is already given to you. Using the state diagram, we have to draw the state table first. So here state assignment is already there because we have assumed previously that there are 4 states. The 4 states are A, B, C, D. But here you don't require any assumption. It is 0, 0, 0, 1, 1, 0, 1, 1. You are at actual binary states. The 4 binary states are under present states. Please note down. 0, 0, 0, 1, 1, 0, 1, 1 are the present states, and you have to create a table like this. And at next state there are 2 options. When x is equal to 0 and x is equal to 1. X is equal to 1, you have separate states. Okay. So x is equal to 0, x is equal to 1, you are having the distinction. So when you are at state 0, 0, please look at this state. When you are at state 0, 0, state 0, 0, when x is equal to 0, please verify the arrow marks, please concentrate. 0, 0 when you are at state 0, 0, when you are at state 0, 0, and when x is equal to 0, when x is equal to 0, so input by output relation we are taking. So when x is equal to 0, you are going to state the same state, 0, 0 state. Please verify this. Okay. When x is equal to 0, x by y, x by y. So when you are at 0, 0 state and x is equal to 0, you are going to stay at the same state 0, 0. So that is what we are representing over here. So when you are at present state 0, 0, the next state is also 0, 0 with output is equal to 0, with output is equal to 0. Next one, when you are at state 0, 0, when you are at state 0, 0, and if your input is equal to 1, if your x is equal to 1, if your x is equal to 1, then you're going to state 1, 0. You're going to state 1, 0. When you're at 0, 0 state and x is equal to 1, you're going to be at state 1, 0 with output is equal to 1. Similarly, you have to write for 0, 1, 1, 0, 1, 1. Okay, I'm going to tell the last one. When you're at state 1, 1, please verify the last one. When you're at state 1, 1 and check the arrow marks, check the direction, and x by y, when x is equal to 0, you're going to the state 0, 0. When you are at 1, 1 state and x is equal to 0, when x is equal to 0, the next state is 0, 0, output is equal to 1, output is equal to 1. Next, when you are at 1, 1 state and x by y, x is equal to 1, takes to the state 1, 0 and output is equal to 0. When you are at 1, 1, x is equal to 1 takes you the state 1, 0 with y is equal to 0. That is how you have to draw the state table. Okay. And then state reduction, you have to check if state reduction is possible or not. This example does not require state reduction. With an example, I'll tell you what is the state reduction. And one more thing, state assignment is also not required because states are already assigned with binary values. If A, B, C, D are given, then only you require the state assignment. So this is how we'll draw state table from state diagram. Next one is you have to understand how many flip-flops that you require. So number of flip-flops required are depending on the number of states. Here the number of states are given as 4. You require number of states as 4. So using this equation we can able to understand that we require 2 flip-flops. You require 2 flip-flops. Okay. And type of flip-flop he has given that it has supposed to be D flip-flop. It is supposed to be D flip-flop. This diagram, this state table, here we have taken x is equal to 0 and x is equal to 1 in 2 different columns. But here we are going to maintain in a single column, and then we have to find K-map and then logic diagram. This I hope till this you're clear. How to draw this excitation table I'll tell you in the next video. Thank you so much.